Welcome to AI Frontiers, where we explore the most exciting developments in artificial intelligence and robotics. Today we're diving into the rapidly evolving world of computer science robotics through 18 groundbreaking research papers, all published on August 25, 2025. These discoveries are reshaping how robots perceive their world, learn from experience, and work alongside humans. Picture this. It's 6 a.m., and a surgical robot is helping a doctor perform delicate heart surgery in Tokyo, while simultaneously, an autonomous vehicle navigates rush-hour traffic in San Francisco, and a bipedal robot walks across uneven terrain in a research lab in Boston. All these scenarios represent the cutting edge of robotics research happening right now, powered by breakthroughs published just yesterday. These machines don't just follow pre-programmed instructions. They learn, adapt, and make split-second decisions that could save lives, prevent accidents, and push the boundaries of what we thought possible. This represents a new era of adaptive robotics, where robots learn from experience and adapt to changing environments in real time. These systems make split-second decisions that save lives and reshape human-robot collaboration. The 18 papers we're examining today reveal technology that's transforming how we think about intelligent machines. Rather than being limited to predetermined behaviors, modern robots are becoming dynamic partners that can handle unexpected situations and continuously improve their performance through experience. Computer science robotics serves as the brain of the robotics world. If traditional mechanical engineering gives robots their muscles and bones, and electrical engineering provides their nervous system, then computer science robotics supplies the intelligence that brings everything together. It's like the difference between a marionette and a living, breathing performer. One follows strings pulled by an external controller, while the other thinks, adapts, and creates in real time. This field sits at the fascinating intersection where abstract algorithms meet physical reality, bridging the gap between pristine mathematical models and the messy, unpredictable reality of our physical environment. The first major theme emerging from these papers is biologically inspired robotics, where researchers turn to nature's 4 billion years of research and development. Just as early aviation pioneers studied birds to understand flight, today's roboticists are mimicking everything from rat learning behaviors to human muscle control. One particularly fascinating example involves researchers creating robots that learn through associative memory, just like rats navigating mazes, but with the efficiency of neuromorphic computing that consumes a fraction of the power of traditional processors. This approach represents accessing the universe's most successful engineering projects and reverse engineering them for artificial systems. The second major theme focuses on advanced sensing and perception systems. Modern robots need to be like supersensory detectives, combining vision, touch, hearing, and even exotic sensing modalities like millimeter-wave radar to understand their environment. Think of it as giving robots not just eyes, but the equivalent of a bloodhound's nose, a bat's echolocation, and a spider's ability to sense vibrations through its web. One breakthrough shows that robots equipped with sensitive skin across their entire body can locate and grasp objects with 85.7% success rate, while being 6 times faster than robots that only have sensors in their fingertips. Safety and robustness from the third critical theme. As robots move from controlled laboratory environments into our homes, hospitals, and highways, ensuring their safe operation becomes paramount. It's like the difference between a stunt driver performing on a closed course versus navigating through a school zone during dismissal. The stakes and complexity increase exponentially. Researchers are developing systems that can handle everything from communication delays to unexpected obstacles, ensuring robots remain safe partners rather than dangerous, unpredictable machines. This transition from laboratory to living room requires robust solutions that work reliably in unpredictable real-world conditions. The research reveals several groundbreaking quantified findings. Perhaps the most significant discovery involves multimodal sensing, where robots using multiple sensing modalities achieve around 88% accuracy in determining where they can safely travel, with improvements of 1.6 to 3.5% over single-sensor approaches. Another breakthrough involves collision rate reduction. Intelligent data sampling strategies can reduce collision rates nearly threefold, from 16% to 5.5%. Neuromorphic approaches to robotic learning enable remarkable efficiency gains, while whole-body sensing creates dramatic performance leaps. Visual reasoning improvements show significantly more coherent predictions and faster learning outcomes. Now let me take you deep into one particularly fascinating paper that exemplifies the cutting edge of robotics research. The work by Jide Zhong and colleagues on FlowVLA represents a fundamental breakthrough in world modeling for robotic systems. The team realized that current vision-language action models were trying to do too much at once, conflating the task of predicting physical motion with rendering visual appearance. It's like asking someone to simultaneously calculate the trajectory of a thrown ball, while also painting a picture of what the ball will look like at each point. Two fundamentally different types of reasoning forced into a single process. Their revolutionary insight was to separate these processes using a visual chain of thought framework. The FlowVLA implementation materializes this separation as an autoregressive transformer that follows a specific pattern. Current visual state leads to flow prediction, leads to future visual state. The intermediate optical flow prediction represents the model's explicit commitment to a motion plan, like showing your work in a math problem. By forcing the model to first predict optical flow, essentially the pattern of motion in the scene, before generating the subsequent visual frame, FlowVLA learns disentangled dynamics that result in more coherent visual predictions. This approach compels models to explicitly separate motion reasoning from visual rendering, leading to more physically plausible outcomes. The experimental results were striking. On challenging robotics manipulation benchmarks, FlowVLA achieved state-of-the-art performance with substantially improved sample efficiency compared to traditional approaches. More importantly, the disentanglement of motion and appearance reasoning led to more physically plausible predictions and faster policy learning. It's like the difference between a student who memorizes formulas versus one who understands the underlying principles. The latter can adapt to new situations much more effectively. This work demonstrates that explicit reasoning about intermediate representations can lead to better learning outcomes, with implications extending far beyond robotics into other domains where complex reasoning can be decomposed into manageable subproblems. Looking toward the future, these advances paint a picture where the boundary between artificial and natural intelligence becomes increasingly blurred. Think of it as watching a river gradually carve a canyon. Each small advance in sensing, learning, and adaptation contributes to a larger transformation reshaping our relationship with technology. The convergence of biologically inspired approaches with advanced AI techniques suggests we're approaching a new era where machines will possess something approaching intuition, the ability to make good decisions quickly in novel situations based on accumulated experience. The democratization of robotics through open-source platforms means innovation will no longer be limited to well-funded institutions, potentially coming from unexpected places fueled by passionate individuals with access to increasingly sophisticated yet affordable tools. Perhaps most exciting is the potential for robots to become true partners rather than just tools. The advances in human-robot interaction and learning suggest a future where robots don't just follow instructions, but understand context, anticipate needs, and adapt to individual preferences. Imagine a world where robots in hospitals don't just deliver medications, but learn to recognize signs of patient distress and respond appropriately, or where robots in homes don't just clean floors, but understand family routines and adapt their behavior to minimize disruption. This transformation represents more than technological progress. It's the emergence of a new form of intelligence combining biological inspiration with artificial computation power. The creation of this content involved several AI systems working together to bring you the latest research insights. GPT Anthropic, CLAUDE-SONNET-4-20250514, was used for synthesis and analysis of the research papers. TTS synthesis was performed using DeepGram technology for natural speech generation. Image generation utilized OpenAI systems to create visual representations. Human expert review was conducted to ensure accuracy and clarity. While we strive for precision, some oversights may exist, and we encourage you to explore the original references provided. This collaborative approach between artificial intelligence and human expertise aims to make complex research accessible to everyone. As we conclude our journey through these remarkable advances in robotics research, remember that the robotics revolution isn't just happening in research labs. It's a transformation that will touch every aspect of human society. By understanding these advances and engaging with the research community, you become part of shaping that future. I encourage you to dive deeper into these papers yourself, many available through open access with code and datasets for hands-on exploration. Share your thoughts about these developments on social media and join the conversation about how these advances will change our daily lives. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.